For this problem is called combinations. We are given two integers n and k, and we have to return all possible combinations of k. So we can choose k elements, k numbers from the range 1 to n, and we can return the answer in any order. So for example, if we have n equal to 4, we can choose from elements starting from 1 up to 4. And we have to choose two of them. So we can choose 1 and 2, 1 and 3, 1 and 4, and so on. In total, there are six total combinations. And in the problem statements, we have that the combinations are unordered. So 1 and 2 and 2 and 1 are considered the same combination. This is crucial information to solve this problem. And the second example is pretty straightforward. It's just one element and one element to choose from, so it's only one combination that we have. For the constraints, n can range from 1 to 20, and k will be in range from 1 up to n elements. Now, the solution to this problem will be similar to the permutation with only slight modification, and that modification will basically reflect this fact that 1 and 2 is equal to 2 and 1 in terms of combination. So they are unordered. Order is not important. These are considered the same combinations. But if we have permutations, order is very important. And 1 and 2 in this order is not equal to 2 and 1. So our solution will basically be the same as the permutations, with only slight modification to the to reflect this fact. As always, we will start by declaring our result. This will be our list of combinations that will return us the final output of the main functions called combine. Next, we will call our helper function, which will be recursively calling to generate all the combinations. Now, we will check in a moment what the parameters that we are sending to this functions are. And at the end, we will just return the result as we set. Next, we will define our helper function, and the signature of helper function is the following. So we have for the first parameter, we have n, which is basically declaring the set of our candidates. So the set of our candidates will range from 1 up to n. And this input we get from the main function. The same goes for the second parameter. K represents the length of the combination. Each combination that we have generated will have the length of k. So we are choosing k elements from the total number of n elements. Next, third parameter is called start, and this is basically our index. This is our index from the permutations problem. This will for each helper function call, it will help us to check from which number can we start in the whole set of them. So if start is equal to 5 and n is equal to 9, for example, we can choose elements from 5 up to 9 in each of the calls of the helper functions. Now, Now, for the current list, the next parameter, the current list is basically representing our current combination that we are generating, and we will add once the requirement is fulfilled, our base case, where the combination length is equal to k, we will just add the current list copy of the current list to the result list. So next we will move to the base case. Now we check if the current list size is equal to k, and if it is, we just copy that list to our main list, the list of all the combinations, and we return from function. That basically means that we are going up the recursion tree. Next, we have the same thing as we had for the permutation. We have for loop to iterate over our candidates, but now you can note that we are not starting from 0. So in permutations, we started from 0 and we went through all the way to the numbers. Like for the first call, for any of the calls of the helper function, we were able to choose any of the candidates. Now, in this case, in our first call, we will be able to start because our start for the first call of the helper function will be equal to 1. We will be able to start with 1 and then all the way up to n. But and we will basically add that each of those candidates and recursively call the helper. But now you can see that we are instead of just passing 1 as a start, we are passing I plus 1. So any successive helper function call will basically have less candidates to choose from. In essence, if we choose the first element in our first call, then we are not able to choose it in any successive call of the helper function. That will prevent us to have basically the same combinations 1 and 2 and 2 and 1, because we are not able to choose the first number at, at at any position. We are able just to choose it in the first position in our first call, or to omit it to generate another combination. So we are just basically, this is the only difference that we have between the permutations and the combinations. And as always, we will backtrack and remove the last element that we have added before calling the helper function, which will basically just be the last element in our current list. So next, for the time complexity, we always have a multiplier. In our case, it's k. Vector k represents the length of the current list, the maximum length of the current list, which is k. And then we have the time complexity for the combinations. Now, for the combinations, we have the basically n factorial, which is the total number that, from which we can choose, divided by the difference between n k, which k represents basically the number of elements that we have to choose, and we have to factorial that difference, times the factorial of the number of elements that we have to choose. Like, this is a standard formula for calculating the number of combinations that we can have. So, for example, if we play with the numbers and have n equal to 4 and k equal to 2, we will have 4 factorial divided by 2 factorial, because 4 minus 2 is 2, times 2, because our k is equal to 2, and that so 4 factorial is basically 1 time 2 times 3 times 4, so starting from 1 up to the number that we are applying the factorial to, and this will basically be 24. So 24 divided by factorial of 2. Factorial of 2 is just 1 times 2, which is 2, and then we will have another 2 factorial, so 2 times 2 is 4, and that will be equal to 6. So the 6 is basically the number of combinations that we can have. For the space complexity, we only have the list, our current list, which is of length k, that we are propagating through the recursion tree, basically generating the combination.